Hello, here we will determine when 2 is a square. Modulo prime. The key tool will be a statement due to Gauss, now called Gauss's lemma. Well, let's imagine a node prime, and let's be a bit more general, and just take not just 2 but any number a which is coprime to p. So then, well, basically not divisible by p. Then this lemma will tell us how to compute the Legendre symbol of that a. So that will be -1 to some number, and yeah, as a Legendre symbol is plus or minus 1, and then this exponent is explained in the statement of the lemma. So to find this exponent, you could take all the multiples of a. Not all really, sorry, I said it wrong. We'll be just taking the first p minus 1/2 multiples of a. So in total I'll just have half of the non-zero numbers modulo p. So that is a subset of non-zero numbers modulo p, half of that, and I could present all the non-zero numbers modulo p by the remainders chosen in this range. So from the negative p minus 1/2 all the way up to the positive p minus 1/2. So that way I will have them place symmetrically the remainders. Then this exponent is just the number of these multiples which are negative, which are in this negative range. So that will be just the intersection of the set of multiples up to p minus 1/2 with the set of negative remainders. So just looking at the multiples up to from the first up to p minus 1/2 and seeing reducing them down to a remainder in this range, and then seeing that how many negative I have, and that will be used as exponent, will be giving me the Legendre symbol. So to prove this, let's first observe that when these numbers are written in this remainder range, they will be all different in the absolute values of those remainders. So disregarding the signs, they will still be all different. So that is equivalent to saying that if I look at those numbers and if I just turn them into remainders in this range, then there will be some sign times 2 all the way up to some sign times p minus 1/2. So these numbers from 1, 2 up to p minus 1/2, they will appear with some sign. So these epsilons are just signs. And that is easy to see, that is straightforward to see just by construction. So let's assume that now there will be not all different in absolute value, so there will be a pair of multiples, so S multiple of A and T multiple of A will have the same modulo P, the same absolute value, so they will agree up to a sign. Well, A is invertible modulo P, so we can cancel it out. So that is really to say that these multiples are either the same or inverse of each other modulo p, but we chose these multiples not to be such. So we chose these multiples really to be different. So that is not possible. Hence, we have this statement that even disregarding the signs, the absolute values of the remainders will be all different. Okay, so now we are ready to prove the Gauss's lemma. So let's look at the product of all these multiples, and just multiplying them all. So I have a times 2a times all the way down to p minus 1 halved a. So that I can regroup into a, and I have p minus 1 halved copies of it, so that will be this power, and then I have the product of 1, 2 up to p minus 1 halved. So that is p minus 1 halved factorial, not to be confused with the Legendre symbol. It's not the Legendre symbol this time, it's just the ordinary fraction, but it is actually an integer, a natural number, and a factorial of that. So that, by the earliest theorem, that is nothing but the Legendre symbol. It is congruent to the Legendre symbol modulo p. So that will be the Legendre symbol with respect to p times the factorial. But knowing that this set of numbers is the same as this set of numbers, I'm done, because now I just take the product of all epsilons, and that is multiplied by the same factorial, by the same product of 1, 2 up to p minus 1 halved. So that is p minus 1 halved factorial again. But that product is exactly this right hand side, because we just need to see how many negative signs we have, and that is counted by nu. So after that is all congruent mod p at this step. So after stripping again the factorials, which are non-zero modulo p, after cancelling them out, we have the statement of the Gauss's lemma. Let me do quick reformulation of that statement, which will be applicable to 2 in the best way. So let's just replace this list of remainders by the ordinary set of remainders, so align them. What we will have is, I'll just write the ordinary set of remainders, and I'll split it in half in the middle, and the middle will be just between these two numbers. And aligning them, so these obviously aligned with themselves, and these are aligned with this bunch in this very way. So p minus 1 is congruent to negative 1 mod p, and all the way down to p plus 1 halved will be congruent to this number modulo p. So now I can say that when I'm looking at counting the number of negative remainders, I could safely say that I'm counting the number of remainders which are larger than p plus 1 if I put the remainders in the standard positive range. So that is my remark here, that the nu can be computed as the intersection of this set of multiples when they brought down to the standard remainders. I will have to count those which are larger than p minus 1 halved. So that is the remark, and now the answer for the question is to s square modulo a given prime. According to this lemma, we just need to count how many multiples of 2 brought down to the standard remainder range are larger than or equal to p plus 1 halved. So we have this answer with nu being this size of the intersection. And yeah, we could basically see which numbers in this set are even and count them, and that will be it. Well, that number is even, p is odd, and then the one 2 steps before is even, and so on. So we just need to see how many steps of 2 fit in this set. And again, the length of the set, well, we're counting from the end of it, but the length is still, so it doesn't matter which way we count, which way we do our hopes, but the total length is p minus 1 half. Right, so we can really parameterize the intersectional numbers as having the form p minus 2 some varying parameter t plus 1. So t being 1 corresponds to this very step, to this very end, and then we are doing steps of 2. And we are going until we run out. So when do we run out? We just need to be in this set, so the p minus 2t plus 1 has to be bigger or equal than p plus 1 halved. So just clearing the denominator, multiplying by 2, we'll have 2p minus 4t plus 2 bounded by p plus 1. Then doing a cancellation, we have p and then plus 1 and negative 4t, which we can put on the other side. And so finally we have the bound for t that p plus 1 over 4 bounds t from above. So t is a natural number. We have to stop just at the integer part of p plus 1 over 4. So that's the cardinality of the set. That is our nu. We have the answer. It is negative 1 to the integer part of p plus 1 over 4. And the final push is to, well, rewrite it in a better form. So if we look at what is this integer part, you could quickly see that it really depends on the remainder of the prime p, sorry, yeah, that's correct, the remainder of the prime p modulo 8. So if p is congruent to plus or minus 1 modulo 8, then if it's minus 1, it just cancels out with the 1 here, and then we have 8k over 4. The integer part will be 2k. If it's plus 1, we'll have 2 plus 8k over 4, which can be written as a 1/2 plus 2k, and still the integer part will be 2k. And then the two remaining cases is when p is 3 plus a multiple of 8, or when p is say negative 3 plus a multiple of 8. And in this case, yeah, we'll have 4, which is 3 plus 1, and then a multiple of 8 divided by 4. So that will be 1 plus 2k. And in this case, we will have negative 2 plus 8k over 4. So that will be, the integer part will be 1 part plus 2k minus 1. But what is important that these numbers are even, and in this case they are odd. And so we have a grouping into two. If p is plus minus 1 mod 8, we have even, so the sign is plus. If the sign here is plus, if p is plus minus 3 mod 8, then we have minus sign here. So that is exactly as the parity is exactly as in this formula. If we compute p squared minus 1 over 8, we will have the same answers. So that is a preferred answer for the symbol. That is what is usually listed as the formula for the Legendre symbol. Well, that's it for now. See you later.